afternoon, ladies and gentlemen. I am Lillie, and today I will be discussing my undergraduate research over cation exchange capacity determination, and this is a comparative study of 3 methods that are currently in use. So the goal of this experiment has been to lower the percent error associated with cation exchange capacity determination. Current methods are only accurate to plus or minus 20% error. So imagine you're developing a landfill liner. Landfill liners are the last defense against allowing heavy metals into the environment. So it's very important to know what kind of clay you're using in your landfill liner. If you're looking at clay that has a 100 milliequivalent per 100 gram CEC, which is the cation exchange capacity, and you test it with one of our 3 methods, the ammonia gas selective electrode method, the ultraviolet visible light method, or the atomic absorption method, and you get a CEC of 80 to 120, it could all still be the same clay. But if it reads as 100 and is actually 80, it will exchange far fewer of those heavy metal ions and allow more of them into the environment when it's put into use, if you've undershot the CEC. So we want our methods to be both precise and accurate, which, because these are older methods, we're hoping that newer technology that we are using will actually result in that increased accuracy and precision. So first you have to know what we're talking about when we mean clay. This isn't the red dirt that you find outside or the red clay in your garden. Our clays are smectites in particular, and in a perfect world, they're going to be produced by 2 tetrahedral sheets containing silicons and an octahedral sheet in the middle containing an aluminum. Unfortunately, this is not a perfect world, and clays undergo isomorphic substitution when they form. This means that silicon in the tetrahedral sheet actually becomes aluminum, and the aluminum in the octahedral sheet becomes either iron or magnesium. There's also, these are repeating layers, and the exchangeable cations fall in between each of these layers. This is the interlayer region. So what is the cation exchange capacity? This is shortened as the CEC and is measured in milliequivalents per 100 grams of clay. The CEC is a physical property of each clay that is dependent on the clay itself. It's the number of negative charges held by the exchange cations, and it reflects the charge deficiency in the interlayer region. When the isomorphic substitution of the clay occurs, it gives the clay a net negative charge, which allows those cations to be exchanged. So why do we care about clays? Well, they're used in landfills, as I've mentioned. They're used in makeup. They're used in developing medications, in building, in various things, even in the shiny paper that magazines are made of. So the precision and accuracy of the methods is currently 20% error. We wanted to see if we can improve on these methods so that they would be more precise and more accurate. The methods that we were looking at are 3 of many, and these were the ion selective electrode, particularly the ammonia gas selective electrode, the ultraviolet visible light spectroscopy, and the atomic absorption spectroscopy. We also get our clays from a standard source clays repository at Purdue. Then these clays are very well studied and characterized over the years so that they are actually a standard. This is why we're able to compare our error to a known quantity. Then we have to purify our clays to ensure that we actually have just the clay that we want, and then we can undergo analysis. So purification occurs through a sedimentation phase where you settle out all of the things that are not clay from the clay. 2 decarbonation phases, a metal removal, and oxidation, an exchange with sodium chloride in order to ensure that the clay is 1 molar sodium chloride, dialysis to remove all extra ions, and you can react the dialysis water with silver nitrate so that a precipitate of silver chloride will come out. And And once we have no more silver chloride removed, then we always go 2 changes of the dialysis water further to ensure that we've removed all of the ions. And then the clay has to be dried. So the first method that we looked at was the ammonia ion selective electrode method. This is the most basic method that has been in use for years, since approximately the 1960s. Again, these are older methods. Originally, the CEC was determined through Spreisinger cesium chromatogram, which was titrating the clay with cesium because clay would strongly absorb the cesium and exchange it very readily. Unfortunately, this required the titration and determining the area under the curve once you had completed this. The ion selective electrode that we used, the ammonia gas ion selective electrode, allowed for a more direct comparison and more simple calculations. There are limitations associated with this method, of course. Given that it is an ion selective electrode, there are ionic interferences. The ammonia gas selective electrode was chosen because it had fewer interferences than a potassium or sodium selective electrode. There is also an issue with concentration versus activity. A higher concentration produces a lower activity. Then there's variable ionic strength, the potential drift that's associated with all electrodes. And the ammonia gas electrode is twitchy on a kinetic level. You had to prepare the clay in order to undergo the ammonia gas selective electrode method. The sodium clay had to be exchanged into ammonium clay and put back through dialysis and dried so that it would be able to react to produce ammonia gas. We had to finally grind our clay, but you had to be very careful trying to grind it because the clay edges could be deformed if undergoing too much grinding, and this could result in jagged edges that would not react very well. So the actual electrode that we used was an Acumet ammonia gas ISE. This was connected to a standard millivoltmeter and then standardized. Unfortunately, this membrane that we have is Teflon, and it's very easily damaged by either touching it or if it comes into contact with the stir bar during reaction. This is why we have to use 200 milliliter tall form beakers in particular, because the stir bar is already very close to the membrane, even in this kind of beaker. We had to create ammonium chloride standards so that we could make a standard curve, and we had to test 3 trials of these standards before we could even do our clay samples, of which we prepared 5. You used approximately 100 milligrams of the clay. You have to know the mass completely, and we added that to 100 milliliters of water. The exact volume has to be known. We stirred the clay until it was well suspended to account for the fact that clays do swell when they touch water. And then we reacted it with sodium hydroxide in excess, a very strong type of sodium hydroxide, and measured the millivolt readout. What we were hoping would fully happen was that the ammonium clay would react with the sodium hydroxide to produce ammonia gas, water, and sodium clay. This way we could count how much of the ammonia gas was released by the millivoltmeter so that we could then determine the CEC. Of course, because of the method that we used, we had to use a standard curve in order to determine what the concentration was of the clay. You got the millivolt readout from the reaction and then put that into your slope-intercept form to determine the log concentration. The log concentration is then used to determine the CEC based off of these calculations. So your millivolt readout goes into the slope-intercept form, you determine concentration, and then you determine the CEC, which is why you have to know exactly how much water you mix your clay with and exactly the mass of the clay. So here are the results of that. This is the percent error of the method. This gives us the accuracy of the method associated with our accepted CEC from those standard clays we got from Purdue. Initially, this was done on the Wyoming clay, and I got approximately 50% error my very first time attempting this. We ran 5 samples of clay while doing this, so that each trial was made up of 5 samples. This allowed us to also have a standard deviation to determine our percent, to determine how precise the method was. As we worked with this method, we got increasingly better results. Anything under 20% was good, and because this is a natural material, we expect error. We expect about 10% error every time that we do it. Some of these work out better than others, and again, the ammonia gas electrode has many issues, including that Teflon membrane being easily damaged, and it being unnoticeable sometimes until you finish all of your trials. So we looked at the standard deviation next to see if maybe the method was at least more precise. It very clearly was, because based on what we are looking at, we actually have relatively low standard deviations. The highest one that we have on here is about a 6, and 6 out of 120 isn't all that bad. So after knowing all of that, we went on to test our spectroscopic methods. These methods require the determination of the concentration of ions left in the solution, not the concentration that's actually in the clay directly. We have to back calculate to get the amount of ion exchanged with the clay. The comparisons that we were able to draw from these methods are like those done with methylene blue and copper ethylene diamine. The methylene blue involved a titration to obtain the total amount of cation replacement, while these methods allowed for the metals to be exchanged and then back calculating to how much was exchanged. So to do the UV-vis and AA methods, you had to do a second exchange with the copper-2 chloride or nickel-2 chloride. We did 100% of the CEC plus another 50% so that we could ensure total exchange and then have metal left over for analysis. We collected the supernatant after the clays were exchanged and filtered it through a 0.45 micron filter. When we did this, we also created a stock solution. We based it solely on the Arizona clay because it had the highest CEC of 120 milliequivalents per 100 grams. And unfortunately, taking the easy way out to not have to do more dishes resulted in skewing the data for the California, Texas, and Wyoming clays higher because clays are very good at adsorbing ions. So our first method of the spectroscopic methods that we used was the UV-vis. We had to create 4 standards in order to determine our wavelength of use, and we found this by using the lambda max of our highest concentrated solution for both copper and nickel. Copper was found at 810 nanometers, and nickel was found at 394 nanometers. This is the standard curve that we produced, and it allowed you to take the absorbance of your analyte to determine concentration, to then determine the cation exchange capacity. Again, this is very simply the concentration of the leftover ion based on the absorbance and slope-intercept form, which you then use that final concentration to back calculate how much was actually exchanged by the clay. The amount exchanged by the clay is then used to determine CEC. And these are the method results that we got here. Again, this is how accurate the method is. This method was originally done on the Arizona clay, and we got a 1.583% error. We did it initially like this to determine if it was worth pursuing these methods to see if they could be refined. Because of this, we were given hope that it would be possible, and we went on to create those stock solutions. Unfortunately, that stock solution of copper resulted in higher percent error and higher CECs based off of the adsorption of the clays. We repeated this with nickel, and once again, we used that stock solution and skewed our end results. So we looked at precision, hoping that maybe it would be more precise, even if it wasn't necessarily accurate. It was in some respects, and in others it wasn't. So this method will have to undergo more refinement in order to know if it's actually usable or not. So after that, we decided to try the atomic absorption spectroscopy. On the AA, we had to dilute our supernatant because because we had to ensure it would be in the linear range between 0.5 ppm and 2 ppm. We also, of course, had to use the copper and nickel hollow cathode lamps because this is the AA and they are very particular to that. And this is our standard curve for the AA. And if you are not using a software that will give you your final concentration, you can again use the absorbance into your slope-intercept form in order to determine how much of the ion was left in solution. Then you have to take into account your dilution factor, and once you take into account the dilution factor, you're able to determine CEC. Because we use a software that gives us our final concentration, we didn't have to plug it into our standard curve, but it's still necessary to have standards when using any of these spectroscopic methods to ensure the instrument is calibrated correctly. And these were our error results for it. This is how accurate our method was. We did not dilute our copper solutions correctly based off of the error that we got. But when we repeated it with nickel, we feel like the method actually showed some prospect of being refined because all of our nickel, well, 3 of our nickel results fell under even 10%. And the California, we can pretty much assume is only as high as it is because the clay did adsorb the metal ions onto its surface, which then resulted in a higher CEC than what it should have been. So we looked at its standard deviation because maybe if it's that accurate, it will be that precise. This was not true. We had some that were relatively precise, but when we went over to the nickel, which showed greater accuracy, we lost our precision. So what we were able to conclude from the AA was that the nickel was able to reduce the error below 20%. It had really good accuracy, but not so great precision. The copper had better precision, but much lower accuracy. We're hoping that by not using a single stock solution of the 120 milliequivalents per 100 grams of clay, we can actually reduce our error to what we would consider acceptable parameters. So the ammonia gas selective electrode was very precise, but not very accurate. And the UV-vis, we have hope of refining it, but the method itself will require more work and looking into. While the AA had both precision and accuracy depending on its metal. So we have hope that these methods can actually be refined, that they can actually be used to determine what type of clay is being used. In the future, we're going to attempt to alter the way that we perform the ammonia gas ISE method so that we can create a uniform particle size without damaging the edges of the clay. And we're hoping that we can close the system for its reaction speed so that we can actually count all of the ammonia gas being released. On the UV-vis and AA, we're going to attempt to make those individual stock solutions. Unfortunately, we're going to have to do more dishes in order to do this. And we're also going to lower our 50% excess to 25% excess for each of the individual clays. We're hoping that by reducing the adsorption of the metal to the clay surfaces, we'll get a more accurate CEC. Because the amount of metal ion adsorbed onto the surface doesn't actually have an effect on the CEC. CEC is only based on the exchanged metal ions. I'd like to thank the Welch Foundation for funding this research, the Department of Chemistry and Biochemistry here at Stephen F. Austin State University, my research advisor, Dr. Alex Bronson, and our department chair, Dr. Michael Schmidt. Thank you. Any questions?
Any questions?
Questions, yeah. On your UV-vis studies, well, and the AA studies, may I ask why you used copper and nickel? We used copper and nickel first because they have a visible color, so that we were able to use them on the UV-vis, as well as because they were inexpensive materials, and we also already had them in the lab.
The reason for your research is to find a better method to find CDC within 20%. Do you know how the standards were measured and how correct they were?
The standards were mostly measured by the ammonia gas selective electrode, I do believe, and so they were within the 20% error. However, they have been repeatedly studied since the 70s or 80s, and we actually have very accurate knowledge of what they are.
Any other questions?
How do you determine if your clays are ground appropriately or if you've damaged the edges?
Human eye is pretty much the way that we do that. We don't have an actual method for determining how finely ground they need to be.
Can you take me through kind of a timeline as far as with your trials you did for the ammonium selective electrode? Because I know on that one, on slide 15, you have a table that has multiple trials. I just noticed kind of a general, for every one, the trials, they usually tend to increase.
This one?
Yeah.
Okay.
So if you kind of look across the row for each trial, as far as just the magnitude of the millivolt response, they generally increase. So when you're measuring this, what's the time? Are you measuring these all in one day?
Yeah, I do 5 samples, so each trial is made up of 5 samples, and I run all 5 samples and all 9 standards at once at the same day.
Okay.
These are all done at the same time, and I do believe that I actually ran an entire set of trials for all 4 clays in one day.
Okay. Do you think that could have any effect on the general increase of your CEC that you're getting out of them? Running, I don't know, maybe the electrode, there's some kind of contamination, because I don't know, what's the cleaning procedure for the electrode in between samples?
You rinse it off with DI water, dry it, and go.
Oh, yeah, okay.
So it very well could be that there is some contamination because these systems are not left closed while they're mixing. We mix them in open air.
Okay.
So there is the possibility flakes from the ceiling could fall into them and be changing it.
Okay, we got time, so let's ask a few more questions. Lillie and Sydney. What are y'all plans after graduation? Y'all are graduating this semester, correct? What are y'all planning?
I'm in the process of applying to pharmacy school, but I'll take a year off and start a little on the ACAT. Take a few prereqs that I haven't taken yet.
I've applied to OSU and their forensics master's program, and barring that, I've actually applied to SFA's master's program. So hopefully I'll be going on to get my master's in chemistry in some form or another.
What did y'all think about the research experience and how that helped y'all?
This is one of the best things that I've gotten out of SFA, being able to get hands-on research experience, being able to have the opportunities to go and do presentations even outside of SFA or at the undergraduate research conference. I feel like it's actually given me an edge over my friends who also majored in chemistry because they didn't have these opportunities.
Things around independence and things. You're given a research project that's up to you on what you do with it and how you go about it in order to get good results. And I guess it builds good.
Y'all both presented off campus, correct? Did one of y'all win an award or something?
We went to the Texas Academy of Science, and I won the best oral presentation for chemistry. I didn't talk to this competition, but I did pretty good last time. And ACS was fun too. It was large scale. And I enjoyed seeing the posters and the area. It was very nice.
Any students in here, any questions about this? Seniors who have done research?
Where are you going to go to farm school?
I need more gelatin capsules.
I'll donate much to you.
I need a big old double hot horse building.
Thank you. Basically, next, I think at 2:30, the post